Hello and good day everyone. We are Group 5 and we will be presenting to you the off-gas treatment section of the off-site facilities. To start off, let me introduce the people who made this presentation possible. Razon Gerald for the intro and overview, Malinis for the details and equipment, and yours truly, Dayap for the flow and PowerPoint presenter. Before we start, let us understand what does this all mean. What is off-site facilities? What are off-site gas treatments, so on and so forth? So let's break it down one by one. Off-site facilities, according to Collins Dictionary, is a facility which is not at the main industrial or commercial site. They are facilities outside that support the refining units. Meaning, in the main refining unit in a certain area, offsite facilities are located away from the main area in order to avoid any possible dangers that the offsite facility may come with it when interacting with the main site facilities. Now, defining off-gas, it is a gas that is produced as a byproduct of an industrial process or that is given off by a manufactured object or material, meaning that these are the byproducts or the waste gases produced by the production or process plants such as carbon dioxide, nitrous oxide, so on and so forth, and we will discuss more about them later. And lastly, when combining both, we have off-gas treatment, or the main reason we have this presentation today. Well, the off-gas treatment are used to treat vapor or gas streams containing petrochemical or chlorinated solvent contamination so that they are safe to discharge to the atmosphere. So in a sense, our waste gas needs to be dispersed in the air in order for it to not harm the people nearing the plant. In order to do that, we cannot just simply disperse the gas just fresh from the process flow. We need to treat them accordingly, dilute them accordingly, so that it would not be harmful when ejecting it to the atmosphere in terms of both environmental and human aspects. And this definition comes from the Enviro Equipment Incorporated. Now, let us discuss the off-gas treatment off-site facilities purpose, or, in layman's terms, the bigger picture. Well, it all comes down to three words: refinery waste management. Pollution is greatly connected to the petroleum refining industry, and refinery waste can be in solid, liquid, or gaseous form. And out of these three, waste air emissions or gas emissions are considered the most difficult to capture and treat due to its properties being in a gas form. This makes air emissions that contribute the largest in terms of untreated waste released in the environment, and one of the most dangerous because it has the ability to bypass even our most strongest defense systems in our body, the immune system, by just simply the size of its matter. By having a small size of air, it can penetrate even the thickest skin, going to the lungs and therefore causing great harm to the human body and essentially in the environment as well. Therefore, we'll also discuss more on the great enemy, which I said earlier, air emissions, or more specifically, hazardous air pollutants. These are chemicals from gas emissions that are known for being carcinogenic and can cause developmental, reproductive, and respiratory conditions. In addition to the workers being exposed to these chemicals, it is potentially harmful to the nearby community and its residents. Without proper mitigation and concern, these could cause the deaths of thousands to millions without proper treatment. And what are these hazardous air pollutants? They come from different forms. They can come from form of a BTEX, or benzene, toluene, ethylbenzene, and xylene compounds. They can also take into the form of particulate matter, or PM. They can also take into the form of nitrogen oxides, the form of carbon monoxides, the form of hydrogen sulfides, the form of sulfur dioxides, the form of other hydrocarbons, and lastly, the form of other like fuels. And we must take note of these hazardous air pollutants because these are what causes the most damage to both the environment and the health of all surrounding the plant itself. Then we discuss, where does it all come from? Why do these come from production plants? Well, it's because they come from the point sources of the plant. The point sources are emissions that exit stacks, or which are the columns that you see in front, and flares which can be monitored and treated. Specifically, they come from the process flow itself, and they are noted as byproduct or waste in material and energy balances. So essentially, point sources emissions are actually noted in the calculations during the planning and operation stage of chemical engineering processes. But those who are not taking note in the material and energy balances are non-point sources. These are fugitive emissions that come from various sources which are typically difficult to locate and treat accordingly, where these emissions can come from different sources, from equipment such as pumps and valves to storage equipment such as tanks and vessels. In a sense, these are accidental emissions, where they can come from leaks or breaks in the pipe systems, or emissions from the pumps or machinery such as gases and smoke. And these are non-point sources because they are not planned to exit the stream. Because we chemical engineers, we need to plan the waste essentially exiting from the process flow. But those who are not planned to exit from the process flow, these are non-point sources, and these are very dangerous. For when we do not account for them, they could cause unprecedented harm to all around the community and essentially the workers inside the plant itself. The next question is, who collects these waste gas itself? Well, we discussed earlier that it came from non-point and point sources. So an example of non-point sources are sulfur recovery units that emit gases that contains hydrogen sulfide, sulfur oxides, and nitrogen oxides. And there is waste gas coming from it. So let's assume that they are fugitive gases, though they are also considered as a point source since it is a part of the material balance that these following gases are removed from them. But in a sense, when the pipes are broken, let's assume that they are non-point. It's a non-point sources, or it's coming from outside or from broken pipes. Then let's have a point source example, which is from the process units itself, such as the cracking unit, coker, hydroprocessing units, hydrotreating units that emit gases containing hydrogen sulfide and light fuel gases. So these are planned wastes. So they are taken note by the material energy balances, and they have its own arrow. So who collects this waste gas itself? Well, they are collected by the waste gas collector systems. They collect waste gas emitted by every process unit and send them to treatment facilities. But the next question is, what is that treatment facility? So here we have the overview of the treatment process. So this is the integrated waste disposal system. So you have different unit operations. From the left side are the feed waste, and is processed in the center, and on the right side, on the rightmost, are the outputs. It might be hard to understand, but it's just trying to divide everything into color schemes. So let's divide the top into yellow, the middle into blue, and the bottom into red. So why did I pick these colors, and why did I specifically choose these sections as divisions? Well, the yellow section is the vapor effluent stream system. They manages the collection of vapor from relief headers and valves, and it collects vapors venting in emergency situations such as absent plant conditions and or plant shutdown. In the middle, which is the blue one, is the light ends feed diversion. It sends the light ends feed to the slop drum, making it bypass the light ends unit. And lastly, the red section, the liquid hydrocarbon drainage, collects the liquid from drain headers, which is used to drain the vessels in emergency situations. But we have off-gas treatment. Our discussion is off-gas treatment, and we will not discuss more on the liquid treatment, but more so we'll only discuss a specification of the off-gas treatment. So this is a more simplified version of what you have seen earlier, and it is all telling a story from how the waste is treated into a harmless waste for dispersal into the atmosphere. So we have the feed, which are gas waste from process units and gas waste from liquid treatments. And we need to convert them into gas waste from process units that are non-harmful and ready to be dispersed into the air, and a byproduct of sewer water. So how do we convert from the left side to the right side? Well, the gas waste from process units will be forwarded to a blow-down drum, while the gas waste from liquid treatments will be forwarded to a water disengaging drum. The outputs from these two are combined and will be subjected into the flare. The flare will be fed steam and water, and the steam will mix with the waste gas as a conduit to be able to be diluted further for a safer transmission to the atmosphere. Hence, gas waste from process units, yellow colored means it's safe to be diluted into the atmosphere due to the presence of steam. In terms of water, same concept. It is diluted. The liquid gas waste from liquid treatments or the liquid treatments, there are still some liquid residue from the gas waste in liquid treatments, and the liquid waste is then further diluted using clean water, and it is now forwarded into the sewer system, or essentially exit the flare as sewer water. So this is essentially a very, very simplified. This is a more complicated. There is a more complicated detailed version, but in simplification and layman's terms, this is the overview of the off-gas treatment. Now, we need to discuss who are the main players of the process, or in similar terms, which of the machines or unit operations serves as the heart and core of the off-gas treatment process itself. Well, going back to the diagram, we can identify three distinct drums: the blowdown or flare knockout drum, the water disengaging drum, and the light ends slop storage drum. So in this discussion, we'll only discuss the blowdown drum and the water disengaging drum, for they contribute the majority of the waste gas that is forwarded to the flare. But for the light end slop storage drum, not as much, because they only serve as a storage to the light end's liquid waste. So to start the discussion, again, the blowdown drum and the water disengaging drum. So the blowdown drum, there are two configurations of the blowdown drum, one of which is the non-condensable configuration. Non-condensable blowdown drums, these drums receive and disengage liquids from safety valve headers to drain headers, and they are often referred to as flare knockout drums, as the disengaged vapor is routed directly to the flare, and it is designed to handle the vapor state and highly volatile liquids, meaning that the vapors going inside will not condense back into liquid, so that it can handle its highly volatile nature. Its counterpart configuration is a condensable blowdown drum. It is compared to the non-condensable one, which is a vertical horizontal tank. The blowdown drum for condensable configuration is a vertical tank, and it is used for the collection and containment of heavier hydrocarbons with low volatility, such as waxy distillates, kerosene, gas oils, and the like. Often, hot steams from operating units and materials above ambient temperatures enter its system, and to handle these materials, the condensable blowdown drum is designed as a direct contact quench drum, whose operation can be summarized by the following series of steps, which will be discussed later on. So you can say that we can think of this as an absorber. So the cooling water flows down from the top, and the gases flows upwards to the vent to the flare header, and it's acting like a simple absorption system, where the water will absorb as much as the waste ends inside the gas waste, or the heavier ends, so that the gas waste will be free from the heavier contaminated ones that is absorbed through the cooling water. And lastly, the water disengaging drum, which is a horizontal tank in nature. It removes any of the volatile and combustible components from certain water effluent streams before they enter the sewer or sour water system, and it is located at a minimum height above grade, operates at about 0.5 pounds per square inch, and vents into the flare system. Pressure and liquid level control are incorporated by free draining the effluent through a suitable seal, and for sour water flash drums, the water should be pumped to sour water tankage. Now, since we know the main equipment considered, we need to discuss how are they sized, or in a way, the rules of thumb for its sizing, or in short, heuristics. Rules of thumb are basically shortcut methods to identify, measure, and calculate the size, shape, and configuration of the drums or equipment being discussed today. Now, for the heuristics of the blowdown drum or a non-condensable configuration, normal liquid surge is based on the daily liquid draw-off to drain per operating day of 24 hours. This includes spillage, sample point draining, etc. The surge capacity between the HLSO or the high-level shut-off for normal drainage and the HLSO for feed diversion should be such as to contain the total feed to a unit routed to this drum for a period sufficient to shut down the unit producing the stream. Should there be more than one unit routed to the drum, then this surge capacity should be for the largest of a single feed stream. The capacity between the highest HLSO and the highest level alarm or HLA should be sized to handle the largest liquid volume that can be discharged in 30 minutes by the relief valves constituting a single risk. The operating pressure for this drum will be about 0.5 pounds per square inch gauge, or that of the water disengaging drum tied to the same flare header. In the case of relief conditions, the pressure in the drum may be substantially higher. Typically, design pressures for these drums is 50 pounds per square inch gauge higher. And in terms of equations, the drum must be sized for a vapor velocity above the HLA at a maximum of 100% of the critical figure calculated by this one. So this equation represents the critical velocity as a function of the liquid density and the vapor density at pounds per cubic feet at drum temperature and at pressure respectively. Next, the heuristics for a condensable configuration of a blowdown drum. The blowdown material enters the bottom, as seen in the figure, of the section drum. Cooling water is introduced at the top of the drum and passes by a series of baffles where it makes direct contact with the hot blowdown stream at the base. So in the figure, the cooling water is on the topmost part of the drum and it is hit with the baffles from the top to the bottom. This allows a greater distribution and in contact with the hot steam going upwards while the cooling water going downwards. Hence, why I say that it is more similar to an absorption unit. The condensable components are condensed in the baffle section of the drum and are carried at the bottom along with the cooling water. This aqueous mixture containing the condensed blowdown then leaves the vessel from the bottom to enter the chemical or oily water sewer for separation treatment. The oily water stream being discussed here is at the bottommost part of the figure. The uncondensed material leaves the top of the vessel and is routed to the flare. In a sense, the condensable vapors are disengaged from the off-gas stream in a process similar to that of absorption, but without the govern of mass transfer, as this process relies on the volatilities of the materials. The following criteria are used to size a blowdown vessel with internal quench. The vapor load on the drum is based on the safety valves constituting the largest single risk. The maximum operating pressure for the drum is usually 1 to 2 pounds per square inch gauge, and the stack may vent to the atmosphere rather than the flare if desired. However, if vented to the atmosphere, the stack should vent at least 10 feet above the highest adjacent structure. Unfired vent stacks are strongly discouraged after multiple fatality incidents related to these stacks. In any case, the vent should not release to atmosphere below 50 feet above grade. Snuffing stream should also be provided. The cooled effluent leaving the drum should be at least 150 Fahrenheit or colder. Water supply should be controlled either by effluent temperature or inlet blowdown stream flow. There should, however, be a bypass flow of water always entering the drum. The drain system from the units to the drum should be free draining into the drum. The drum therefore should be located at a minimum height to grade, where very waxy materials are likely to be handled. Steam tracing off lines and a steam coil in the drum should be considered. And lastly, the heuristics for the water disengaging drum. The following streams should be directed into the water disengaging drum. All water from distillate drums, which have been in direct contact with flammable materials such as light hydrocarbons, is sent to the disengaging drum before disposal to the sewer, except for when a sour water stripper is included in the plant, as these streams are sent into the stripper. Cooling water drainage from coolers and condensers and the steam condensate streams, which may have been contaminated with flammable, highly volatile material, is sent to the disengaging drum. The vapor load on the drum will be the result of high volatile material flashing to equilibrium conditions at the drum pressure. This design load is based on the largest amount of vapor arising from a single contingency. For example, for exchanges for this contingency would be due to a fractured tube. For liquid from a distillate drum, this will be due to a failed open control valve on the water outlet. The liquid seal must be such as to eliminate air from the sewer system and to allow free drainage from the drum. An oil or chemical skimming valve is located at the water NLL. This allows for the draw off of the oil phase from time to time. A high interface level alarm is often included as a means for process safety. Knowing the equipment, the process overview, and how we size them, we then need to discuss what are the standards in order for off-gas treated to be able to be dispersed into the atmosphere, or the ideal emission of gases. So of course, before we subject anything to the environment, they must be regulated and monitored. This is done by basing it on the U.S. petroleum refineries found on Table 17.3 of the Book of Fahim and Al-Sahaf of the Fundamentals of Petroleum Refinery by Elsevier. So, in this table, it composes of the emission regulations where for catalytic cracker units are emissions that are organic, hazardous air pollutants. Regulation must be below 20 parts per million volume or 98% by weight. For the emission source from the catalytic cracker, whose emission is inorganic hazardous air pollutants, proposed regulation is 500 parts per million volume dry, and particulate emissions below 1 pound per 1,000 pound of coke burn off or nickel emissions below 0.029 pound per hour. Lastly, from the emission source of a catalytic reformer, coke burn off or catalyst regeneration, its emission is hydrochloric acid. Its proposed regulation must be below 30 parts per million volume or 92% removal weight efficiency. And we discussed everything, but the most important thing is in terms of monetary value, or how much does everything cost in terms of utility, in terms of electricity, in terms of operation, so on and so forth. Hence, in this section, we will discuss the economics of the process. Now, keep in mind that we the researchers cannot find an exact study on the economics of an off-gas waste treatment facility, so we based the economics in terms of a known study of a flue gas treatment with a 10 megawatt boiler. Since essentially, theoretically, they both do the same treatment parts of the off-gas, we will use this as basis to have a good understanding on how much does the off-gas treatment, which was discussed earlier, could actually be in terms of, again, utility, monetary value, and etc. So this is the process basis. And a study by Audibert in his book of Waste Engine Oils, he studied the economic analysis of the 10 megawatt boiler gas treatment facility. And with an investment cost of, and with a redeemable capital of $747,500, raw materials for waste oil $50 per ton of feed, and reactant purchase of $4.42 per ton of feed. Consumption of utilities is 6 kilowatt hours per ton of feed. Very, very high. And total variable cost is 60.4. Let's skip now to the maintenance. Maintenance, 3% of investment. And of course, we need to know the profit. So that's the main thing that we want to know. The profitability of waste treatment or off-gas treatment. So the profit before tax is around $2 million, and the cash flow is also around $2 million, with a return on investment in percentage 273%, so very, very high, and the payout is 0.4. Annual tonnage of waste oil burned 16,000 tons per year, very large. A boiler heat output of 20 megawatts and a payout of 0.2 years. So knowing that this amount of money is needed just to treat off gases without even considering the liquid waste and the solid waste produced by the refinery is actually a great amount to be discussed that needs further attention if one wants to invest in refining equipment and refining processes. Because in refining processes, you cannot just only invest in the process on getting oil from crude parts. You need to take note from each step, from the collection to the treatment to the process, and lastly to the waste. And the waste is as important from the process, because without considering the waste, our environment around the plant and essentially the entire world would come crumbling down. So with proper waste treatment comes a happier environment and a higher quality of product. And these are our references that we based on for all the information that was presented earlier. The books of Al-Sahaf, the books of Priliao, the books of Tries, and the books of Audibert from the Fundamentals of Petroleum Refining, Environmental Impact of the Petroleum Industry, Handbook of Petroleum Processing, and the Waste Engine Oils book, respectively, in their respective authors. And again, I am Ron Dayap, the representative of Group 5, who presented to you the off-gas treatment off-site facilities. Thank you and good day.